if we have a better look about this statistical reconstruction of sea level change, we might have some information here. Okay, so although this statistical reconstruction have really nice fit to the data temporally, if we check this sea level change spatially, maybe because we are lacking of data, because we only have sea level data in coastal area, and we only have sea level data for location where we have some potential to have sea level data, for location where it's not so much growth, something like that. So we have limited spatial coverage. So the spatial reconstruction of sea level change do not necessarily reflect our physical knowledge of sea level change. We know the process of GIA, but we would expect something like sea level is falling in here, but something because of the existence of Laurentide ice sheet. And we know that the uncertainty, if we incorporate physical knowledge, the uncertainty wouldn't look like that. It might have some physical parameter uncertainty in those techniques. Okay, I see. Okay, Sarah is leaving. It's okay. Okay, good to see you, Sarah. So let me go through that. So, and also another problem is that this kind of statistical method cannot capture the teleconnections, right? So the teleconnections means if you melt an ice sheet in Antarctica, it will have a strong negative correlation between the Antarctica sea level change and the North America, because Antarctic sea level is falling because of the gravity, and the North American ice sheet, North American sea level is rising because of the Antarctic ice melt, right? This kind of statistical method is hard to capture those teleconnections. So in this case, that's try to harness physical models in our GP models. So the physical model I'm using here is a GIA model, so glacial isostatic adjustment. So I wouldn't have the time to go through those, but if you are interested in, you just search glacial isostatic adjustment, which is kind of one of the most commonly used model to describe sea level change for historical geological sea level change. Okay, so let's imagine we have an axis that from the left hand, we have a pure statistical model. For the right hand, we have the pure physical model. Okay, so I will give you 4 examples here to let you understand slightly better how do we incorporate more and more physical model in our GP model. Okay, the first model is that is the model we discussed before, which is I have only a GP model. I use zero mean and I use a statistically reconstructed kernel, which is we talked about before, a global one, a regional nonlinear one, and a local nonlinear one. Okay, in the second model, I use a GIA model as our main function, and I use a kernel, a statistical kernel, as we used before. But now I assume the global sea level change signal is embedded by my GIA model, so I only use a regional nonlinear and local nonlinear kernel in my model too. Okay, so in this case, because I was incorporating a mean function, the covariance function here is basically modeling the residual between the mean function and the observation. And then the model 3 is that I still use a zero mean function, but I use a sampling covariance function. So here, the sampling covariance function is basically you just directly calculate the covariance between different set of your GIA model. So for GIA model, you can change your ice sheet parameter, you can change your solid earth parameter, so you have a lot of GIA model predictions. And you can just directly sample link the covariance between this GIA model to build a sampling covariance function like that. And then I use a taper here, a temporal taper here, because if you in your GIA model, if you know the sea level will look like 8,000 years ago, maybe that GIA model can directly corresponding to the sea level change signal. So let me draw a diagram to show you. So the GIA model basically sometimes look like that, right? Just an example. So if you kind of know this sea level here from the observation, you kind of already know sea level is here later in time, right? Because you do not sample enough ice sheet model, so you are covering really limited temporal uncertainty for this sea level change. So what we actually do here is like we are kind of decreasing the temporal covariance by the physical model. So what we tell the model is that if I know the sea level here, I only know the sea level 3,000. I use 3,000 years, several thousand years. You can change this parameter here to let the model tells, okay, if I know the sea level here, I only know the sea level several thousand years after several thousand years before this data point. Okay, so this makes our model more flexible. This is what we call the temporal taper. And lastly, we have model 4. That was a pure GIA model. So we are kind of generating a weighted combination of this GIA model through this weighting parameter. And this weighting parameter, we assume, is a Dirichlet distribution, which will give you some random weighting factor that will sum to 1. Okay, so let's see how we do this 4 model in PaleoSTEHM. Okay. So to do the so we already do the first model. This is what we did before, right? So let's try to do the second model. So let's load I60. So I7G actually. So I download the I7G sea level data, and you can kind of use I7G as your main function. So actually, what you do is you calculate I7G prediction at each sea level data point, and you calculate the residual. So then you can use this residual to input in our GP model. So our GP model is basically using covariance function to model this residual across space and time. Okay. So what you do here is you set 2 kernel, regional nonlinear and local nonlinear, and you calculate the Y residual here. You calculate the Y residual. So which basically is the observation minus I7G prediction, and you input Y residual here in the GP model. Okay, so I think the prediction. Let's just run 20 iteration to see if that can work out. Okay, because it's kind of it's because we have more data, so it's kind of it's 3 to 4 seconds per iteration, so it might take you some time to run through that. But just run 20 iteration to demonstrate it. Okay, so you can run this kind of 20 iteration in your collab as well. But again, like if you want to run the project, maybe you want to run 1,000 iteration in your local computer. Okay, so after 55 seconds, you see that our loss function is still decreasing, but that's fine. We're just using this kind of hyperparameter for testing purposes. Okay, so let's now start to generate some prediction based on our model 2. So again, model 2, you see the green curve shows you the I7G prediction, and the blue curve shows you the GP model prediction. So it's kind of the combination between the GIA model and GP model, and this is the rate. So then, okay, so you can start to interpret your GP model prediction. What's the difference between your GP model and your GIA model? So maybe there's something caused by some physical signal you do not consider in your GIA model, or maybe some parameter bias in your GIA model. Okay. And then we can predict that spatially as well. So let me try to make it 3.5. This one here. Okay, it works. Okay, so now if you are running a high resolution, it looks like that. So it's kind of already incorporating the GIA physics in this prediction, right? So the GIA prediction will provide the GIA physics here. So you have a North American ice sheet here, so sea level is much higher here compared to the south. And the GP model basically predict the residual between here the GIA model and the observation. So it provides you some residual information, and you add them together, you have the overall prediction. And this, because we are using the GIA model as we are using one GIA model as our main function, there is no GIA uncertainty included in this model as well. So the uncertainty here still depends on the availability of the data. Okay. Okay, I hope you are able to run this model. Maybe I'll give you 2 minutes, 2 minutes maybe, to run this model. Maybe you can start to increase the temporal resolution a bit, but it maybe work in 3 degree or 2 degree. But it might kill your terminal as well. Okay, so next thing is like, let's generate some sampling covariance function. As I said before, we try to generate some sampling covariance between different fit GIA models. So now I am trying to get a model from the ANU model and one GIA model from Ivan Gowan 2021 paper. And to increase the sample size, I just generate some synthetic GIA prediction by enlarging and by making enlarging or shrinking this GIA prediction by 1.5 for each of 3 GIA model. So now we have 9 GIA model. So here you can see the sampling covariance between this 9 GIA model. This is an unweighted version. So this covariance function do not consider which GIA model fits better with the sea level data. And this is the weighted covariance function. So I assign higher weighting for those better performing model. Okay. So then let's try to use it in our GP model here. So here I just make each GIA model as a interpolation function, a 3D interpolation function. So you can kind of you can kind of inputting three-dimensional values into this model. Okay. Maybe. Let me try to do that. Okay, so let me try to see how the interpolation works. Okay, X new. Okay, you can kind of input this kind of three-dimensional value into this interpolation value. So this will give you the prediction by this data, by this GIA model, right? So the GIA model is basically a 3D interpolation function. Okay, so I give all of my GIA model into this model ensemble list, and I input this model ensemble list into what we call a sampling kernel. And I give us temporal taper of 2,000 years to reduce the temporal correlation, as I said before. Okay, let's do that now. So, no course. Okay, so I think this is maybe a code error. So maybe let's just using this one now. Okay. Really, I'm not quite sure why, but let me try to do that in my local computer. So I'll try to fix that code later. Okay, so let's do that now. Here. Okay, so everything is pretty much the same. So maybe I will update with you to fix the bug, so you can run that later. But today probably you don't want to run model speed here. But the syntax is quite the same. There's just some technical issues in the optimization algorithm. I'll fix that soon. But if you do that, you can start to generate some predictions, right? And temporally, you can see that because we are incorporating the physical knowledge, this kind of prediction not always fit well with the sea level data, because we need to maintain the physical knowledge of spatial distribution of the sea level across different area. And let's try to predict that in space, right? Because we are kind of building this covariance by physical models. Now the spatial prediction have some physical meaning in this prediction. So you can see that in the area where some ice sheet, you have some higher sea level, whereas for the southern location, the sea level was much lower. And the standard deviation quantified by this GP model is actually reflects on physics, where we have a higher uncertainty in the north and lower uncertainty in the south. Okay, the syntax is exactly the same. You just generate a prediction matrix, which is a three-dimension, a three column data to tell the model which location and which time you want to predict sea level. Okay. So because maybe you cannot run this model, so let me just jump to another last one model. The last one model is kind of the pure physical model. So it's kind of just like a calibration of the physical model. So in this case, we calculate the misfit here to quantify which physical model fit the data better, and we are kind of set our prior for the weighting function. Okay, the better model has the higher weighting prior. Okay, so which is alpha here. So to build a GIA model here, a physical GIA model here, you use the GIA ensemble model as a main function, and you input the main model ensemble as we defined before, which is here. You just input several interpretation function as a model ensemble. See here, and then we just set a Dirichlet distribution as our prior as a weighting parameter, because Dirichlet have a nice property that all of the weighting values sum to 1, which is what we want. Okay, so let's try to run it with 50 iteration to make it quicker. Okay, so after 50 iteration, so we can now start to generate to see that it's kind of still really large misfit, because we are using GIA model here only. We do not incorporate Gaussian process, so the GIA model do not necessarily fit data well. Okay, so let's now to generate some prediction. So okay, let's try to fix this error here. So because we are calculating between torch and NumPy, so usually sometimes you need to convert the data structure from torch to NumPy. So the torch is a data structure that you can support GPU acceleration, those kind of things. But NumPy is like what we usually do for processing data in Python. Okay, so here is like you can see the weighting for each GIA model. So this kind of weighting maybe not that good. So if you see here, it's my previous optimization result. You see that there are several GIA models fit significantly better than other GIA models. So that's why this set of GIA model have larger weighting. Okay, so then again, the syntax is exactly the same. You can use this syntax to generate some GIA model prediction, as you can see here. So the GIA model, not necessarily fits well with the C-level data because maybe we are sampling not enough the physical parameter space. So the GIA model may try to fit other sites with more data. So this site do not fit really well. But this kind of GIA model is like, because we are directly combining different GIA models together, so we can make direct interpretation of the physical parameter. So for example, we can make direct interpretation of what is the ice sheet model using this combined GIA model, what is the Earth model, something like that. And you see that the GIA model do reflect the physics pretty well. Okay. So hope this makes sense to you. And lastly, we can kind of compare 4 different methods in terms of their prediction in spatial data, temporal data, and how does they quantify the uncertainty differently. It's kind of, again, like, none of this model is the best one. It kind of depends on what you want to do in your project, and you can make your own specific choices. Okay, what kind of model I want to use in my project. It's kind of moving from the pure statistical model, which perform really well to feed the data, but it's not necessarily tell you the physics of sea level change. But if you move into the pure end of your GIA model, it tells you really well with the underlying physics, but it might not necessarily fit the data well. and you have some intermediate choices between this pure physics and pure statistics spectrum. Okay, I hope you can run that model. So maybe I can give you several minutes to run that model, and our last content in this workshop is I will go through a specific project using Gaussian process to reconstruct global mean sea level in the Coleman era by Bob Cobb 2016. And